Hello, welcome back to the channel. So in this video we'll see some important aspects of actinoids and even some chemistry of uranium, keeping CSIR-NET examination in mind. So questions related to uranium totally to this category, say some 5-6 questions can be found, and much of them they are related to this uranium itself. So let us see something about uranium chemistry too. But before that we shall see which are the actinoids and some basic aspects of actinoids. So actinoids, this is a 5F series as we all know. So it starts with, in fact, it is said to be from 90 thorium to 103 lawrencium. But all these elements, they will be followed by actinium AC element with atomic number 89. And because of properties, similarity in properties, all these they are called as actinoids. One very important feature of this is that all these are radioactive. Unlike 4F series, in case of 4F series, it was only promethium which was radioactive. But here, all these elements, all are radioactive elements. That is one reason why chemistry of actinoids, it is not explored. Handling these radioactive elements, it goes difficult, right? And one more thing, they are not that easily available. Trans uranium elements, much of them they are synthetic, most of them they are synthetic, and that is the other reason why chemistry of actinoids, it is not still explored. But all this, including actinium, all 15 actinoids are known. So which are those elements, and some basic aspects, how to remember that, how to remember the names of actinoids, that those aspects we shall see. Right, so here as you can find, so it starts with 89 actinium, and then up to say thorium, protactinium, uranium, neptunium, plutonium, americium, curium, berkelium. See, curium symbol, it should be kept in mind. Curium is Cm because there is one more element, californium. So which is from this series itself, californium. Here you can find that californium is Cf. So after curium, it will be berkelium, then einsteinium, fermium, mendelevium, nobelium, and lawrencium. Uh, it's not that necessary to remember this series questions from CSIR point of view. If we know 4F series, that is sufficient, but still we can try to remember the series as it is. And here, as we do in the case of D block elements, which element falls below which element. In that way, also, even if we remember, that will be of limited use, because properties of 4F series elements and properties of 5F series elements, there are a lot of differences. And just by remembering the electronic configuration of 4F series, we cannot write the electronic configuration of this 5F series. So because of all those things, we can remember, say, actinium to lawrencium in a sequence, it's good. Otherwise also it's not a problem. And symbols I have given here, and important symbols where there are chances for confusion, that also I have said, right? So these symbols and names, it is better if you can remember them. Next thing, there is a mnemonic using which you can remember this whole series. That mnemonic, it can be divided into 3 parts. The first, it starts from these 3 planets, Uranus, Neptune, Pluto. 3 planets, Uranus, Neptune, Pluto. Of course, these 3 elements, which are those uranium, neptunium, and plutonium, they have been named after the planets itself. Then next, America cured Berkeley in California. America cured Berkeley in California. So name of cities, America, of course country. Then America, this is named after scientist Curium. Curium, it is named after scientist Curie. Cured Berkeley, again it is name of city, and California, it is name of city. Then it is just name of some scientists. Say Einstein, Fermi, and Mendel are Nobel laureates, or were Nobel laureates. So this can be remembered very easily. Einstein, Fermi, Mendeleev were Nobel laureates, where it is just to complete the sentence. So in this way, it is possible to remember the whole series at a stretch, wherever if it is necessary. In that case, we can just to recall this whole series, it can be done. Further, electronic configuration, as I said, it's not that easy to remember, and even there are the ground state electronic configuration of all these elements. Still, it is doubtful. It's because energy difference between this 5F, and here we will be having 5F and 6D shells filled, and this 5F and 6D shell energy almost it is equal. So therefore, sometimes electron can go to 6D, and sometimes so it can even go to 5F. So in a series, writing electronic configuration, it is little difficult. If at all it is needed, then we should just remember ground state electronic configurations. It must be remembered, but I don't think so it is necessary. In general, what can be said is that, say, it follows this radon. Then 5F 0 to 14, any electron count can be there, and D Sometimes even 2 electrons, instead of going to 5f, they can go to 6d. And 7s2, this is common, just as we had 6s2 common in the case of 4f series. So here it will be 7s2, which is common. Only this is certain. Everything else it is uncertain. If you can just refer to any books, you can find the electronic configuration, and book to book electronic configuration of these elements, definitely it may change. So therefore I have not gone to give electronic configurations. And even in particular oxidation state, here also 3 plus is okay, common oxidation state. That also a bit difficult, giving electronic configuration in 3 plus, because 3 plus it is not stable oxidation state for all lanthanoids. There are some other oxidation states which are more stable than 3 plus. So therefore when that has not been given here. So just if you can remember the whole series of elements, that's fine, that's sufficient. Fine. Next, some properties. In brief, we shall see properties of all these elements. First one, ionic size. Again, here also you can find a gradual decrease, as in the case of 4f series we can find gradual decrease, but it's up to midway, up to say californium, you can find that decrease. And the reason behind this, again, it is said to be something called as actinoid contraction, as we had lanthanoid contraction in case of lanthanoids. So here we have something called as actinoid contraction, right? But after that, after midway, size it is lesser than expected. So uniform trend it is not followed after californium. And the reason behind this, 5f being subsequently filled, and in this case what happens is that actinoid contraction it is greater than lanthanoid magnitude wise if you look at, and therefore this 5f orbitals, they cause still poor shielding, and that's the reason why this size is in case of actinoids that is said to be decreasing. But the trend is not uniform. Up to say californium it is okay, then further size it is smaller than what we expected. Fine. Next, oxidation states. Coming to oxidation states, +3 to +7, almost all +3, +4, +5, +7 oxidation states they can be observed. And as I've said, among that +3 is common. +3 it is shown by each and every element, right? But this +3 to +7 oxidation state, so this variety of oxidation states, it is just up to say again americium till midway. So americium and californium almost they fall in the middle of the series. Say till americium you can observe this variety of oxidation states. So just like in the case of 3D series, up to Mn you can find even oxidation state plus up to +7. So all different possible oxidation states it will be possible, and number of possible oxidation state that goes on increasing till midway. Same trend is observed here, right? So in that way till americium these elements they resemble transition metals in variety of oxidation states. After that, even in the case of 3D series, you notice the same thing, that after that much variety of oxidation states, usually it variety of oxidation state it decreases. Something of that kind itself here it can be observed, right? And limited number of oxidation states will be there after americium. So therefore usually what is said is that till midway they resemble transition metals, afterwards they resemble lanthanoids. And in fact this fact it is even reflected in their absorption spectra. So absorption spectra of this 5f series it can be divided into two categories. Say up to americium the behavior or electronic spectra it will resemble like transition metals, and after that it resembles that of lanthanoids, and something same trend it can be observed in the case of oxidation states too, right? And one more point, +3 it gets stabilized after curium. After curium, next elements +3 oxidation state it gets more and more stabilized till the end of the series. Okay, that is briefly about oxidation states. Then briefly about coordination chemistry. So tendency to form complexes, if we look at, definitely these have got more tendency to form complexes than lanthanoids. Coordination chemistry it is not much explored because of non-availability of and radioactivity of these elements. But in general we can say their tendency to form complexes it's more than lanthanoids, right? And even in this case, just like in the case of lanthanoids, we can observe more large coordination numbers. Usually it will be greater than 6 itself. And very important difference between 4f complexes and 5f complexes is that, so 4f complexes it was much ionic interaction between ligand and metal ion, but here some kind of covalent character it is expected, or covalent character it is observed between metal ion and ligands. It is because of 5f nature of 5f orbitals. So 4f if you consider they are not much diffused. So here 5f orbitals they are much diffused when compared to 4f. So because of which this 5f orbitals, you can expect them to participate easily in covalent bonding, and because of these covalent bonds, they are directional, and they are much covalent as compared to that of 4f bonding. Fine, next absorption spectra. Here also FF transitions are possible, and mainly FF transitions they are because of this 5F to 5F electrons will move from 5F to 5F, right? And transitions as compared to that of 4F. 4F it was sharp transitions, and intensity of transitions it used to be usually very less in case of 4F series. But in this way, in that way, here it is reverse, broader transitions, just like though it is not as broad as in the case of D block, you can expect broader compared to 4F. Definitely these transitions, they are broader transitions and intense transitions. And reason behind this is because metal ligand interaction being much covalent, so those vibrations they makes the transitions broader and intense. Next, absorption spectra, it is affected by ligands because of covalent character. So change in ligand environment that affects absorption spectra. Unlike in the case of 4F, there was very little interaction, ML interaction, because of which ligand environment, change in ligand environment, that had not caused much changes in the absorption spectra. But here it is not so. Some change in absorption spectra can be observed because of ligands, right? So this point already it has been said. So lighter actinoids. So first half of the series, in 3+ oxidation state, their absorption spectra it will be just like transition metal like, and the later half 3+ heavy actinoids, they produce spectra which resembles to that of lanthanoids for F series. Fine. Last thing, magnetic properties, it's very difficult to predict. In case of lanthanoids, say mu-J formula, that is considering spin orbit coupling, it was possible to predict magnetic properties except for 1 or 2. But here it is very difficult to predict magnetic properties. The reason behind this is that, so here both spin orbit coupling, that is also dominates, or that is also of equal importance, and even ligand field effects, they are there. So in case of lanthanoids, these ligand field effects, they were minimum, because of which based on the spin orbit coupling formula, it was possible to predict. Say where we go to 3D series and all, there just we consider ligand field effects and this spin orbit coupling being negligible. So based on this, it was possible to predict magnetic properties. But here both they are of almost equal magnitude, both dominant, and that's how which equation is to be used. Definitely that will be under discussion always, and it is difficult to predict their magnetic properties. Okay, so that is about just in very brief, have just introduced you to actinoids. Now we shall see something about chemistry of uranium. So chemistry of uranium compared to other elements, chemistry of thorium and uranium, it is much explored. But we have more questions related to uranium. So some points about uranium complexes that we shall see. First thing, uranium, it can exist in different variety of oxidation states, starting from uranium 3+ to it can go up to even uranium 6+. And 6+ it's maximum possible oxidation state. So all 5F electrons and then all valence electrons, if they are removed, so uranium it can be taken up to 6+ oxidation state. Uranium in its 3+ oxidation state, it is powerfully reducing. Why it is powerfully reducing? Definitely we can understand it easily. Say it can undergo oxidation. So if it has to undergo oxidation, it can donate electrons to some other species. Therefore this is a powerful reducing agent in aqueous medium, right? And uranium 5, if you consider uranium in its 5 oxidation state, it can undergo disproportionation, because oxidation is also possible for this oxidation state, and even reduction is possible for uranium in 5+ oxidation state. So it can show disproportionation reactions. And some important oxides of uranium, if at all they are to be named, UO2, UO3 and U3O8. These are some important oxides of uranium. And this UO3 is very important species, because UO3 in acidic medium, it will produce a species called as uranyl, which stands for UO2 2+, where oxidation state of uranium it will be +6. You can just work it out. So no change in oxidation state here. So here also uranium it is in 6+ oxidation state itself, same as when retained here. So this species uranyl, this is very important, because this uranyl species it can form complexes very easily. Much complexes of uranium, they are uranyl complexes, right? So this uranyl unit, it is linear covalent dioxido unit. It is linear, and definitely it is stable unit, and covalent bonding is there between uranium and oxygen in this case. Then next, this uranyl species, it will give you yellow coloration when you have uranyl ions in solution, you can get yellow solution, yellow coloration. Yellow coloration, it is due to definitely not FF transitions here, because uranium, it is in 6 plus oxidation state, so no F electrons, no D electrons, nothing. So DD transitions or FF transitions, they are not possible. So what you can think of is definitely see this uranium, it is in highest oxidation state, and therefore it should be LMCT, say just like MnO4 MnO4 minus or CrO4 2 minus, like that. So manganate and chromate ions or dichromate ions, how they show LMCT, in similar way LMCT transitions, they are expected in case of uranyl. Next, in uranyl complexes, sorry, this is not uranyl, UO2 plus. UO2 2 plus is uranyl. I think I have missed 2 here. So in both these cases, it should have been UO2 2 plus. Let me just correct it. So this should be uranyl 2 plus, and even in this case, uranyl 2 plus it is. And uranium, it can form one more species, UO2 plus, right? Here also definitely it is UO2 plus itself, uranyl. Okay. Other ligands, see these two oxide ligands, how they occupy is they form a linear unit. Say, if at all I have to draw uranium, it is here, double bond O, and say double bond O, something like this, and overall it is 2 plus charge. This is your uranyl unit. So other ligands, they occupy these positions which can be called as equatorial positions, and everywhere here you can expect near equatorial position or equatorial positions other ligands to occupy, right? And uranium, it can even give organometallic compounds. One such example has been given here. It can link itself with 4 cyclopentene rings to form this kind of compounds. And there is one more very important concept, complex, known as uranosine. Uranosine, it's just like ferrocene, but in case of ferrocene, it is 5-membered ring. Here it is 8-membered ring, eta 8 cyclooctatetraene. COT, it stands for cyclooctatetraene. So that can form a sandwich compound of uranium, just like ferrocene, which is known as uranosine, right? Even thorium, thorocene, it can form, but this uranosine, it is of much importance. So I have just tried to cover some basic aspects, keeping previous appeared examination questions in mind, some basic aspects whatever of actinoids and uranium, whatever are required to answer the questions. Okay, in the next video, I shall consider all the questions which have appeared in CSIR-NET examination related to. And if you have not subscribed to this channel, please subscribe, and you can keep updated about this channel by pressing bell icon to get the notifications, and you can share or you can recommend these videos to your friends. If you like this video, please you can give a like to this video. Thank you for watching. Thank you again.